In total, if you have m sleeps for the map to sleep based on the input, and r output based on the reducer for the keys, right? In the middle, you will have m times r partitions, right? We need to do. So to go to the system, right? So the Google file system will go into, for each sleep split, you go to one of the worker, and the worker will read the data from the disk, and then write the intermediate result to the disk again. And so each mapper will have the same map function, and the reducer will read the intermediate data from the disk, and then to apply the reduce function to get the final output. The master node, this master node is for map reduce, will coordinate both the marker and also the shuffle, the communication among them. So there are total m plus r task stages, right? M workers and r tasks, and m times r state, right, for different other locations. So the improvement they do is that for performance, right, there may be some stragglers, as I told you previously. But most of the tasks already finished, but we are still waiting for one or two mappers to be finished, right? So what they do is that they will duplicate those tasks and try to finish them quickly. And they can also skip some bad record. Right? So if you have some failure, skip them, right? So that you can finish the job as quickly as possible. So they provide some utilities, right? You can do the sort inside the partition, right? This is similar to when you learn the algorithm, right? Many algorithms you need to sort, right? So this gives you a lot of benefit for later search and other operations. You can also combine, right? Locally, you can already do some partial reduce, so that the data you communicate may be much smaller. You may have additional output and status information, counters, and for debugging and for other purposes. Right. Okay, let's see the performance of this. The horizontal axis here is the seconds, and the y-axis is the input. Right. You can see they read the data in, right? So they do a lot of local operation to have, they have a 1,800 machines. They read 1 terabyte of data at the peak of 31 gigabytes per second. Right? This is fairly fast at that stage. This is when Google published the papers roughly 10 years ago. Right? So, but without local optimization, locality optimization, they can only reach 10 gigabytes per second. Right? So what does the locality means? Right? So you try to co-locate your map with your data, right? So that you don't need to move the data across the network. Because the network, the red switch, the capacity is only 10 gigabytes per second. But if you don't need the networking, then you can go to a peak that is much faster than that one. Also, you see here, at the beginning, there is a slow start stage, right? So that is a bottleneck. Right? Especially if it's a short job, that part hurt a lot. Right? Later, their paper work out data center TCP, trying to make this part fast. Okay, here is the performance. The first column is for normal operations. We see here the first lines are for map. Second is shuffle communication. The last one is a reduce. You see, first they read the data in, finish roughly at 200 seconds. Even they are working on the reduce, the shuffle stage already started. Because if you already get some result, you can start to send it out. Then the output finish start after 200 milliseconds, and it's finished finally around 800 seconds, 839 seconds. So this is a normal operation. So the middle column is that if there is no backup task, which means the to fight for the stragglers, right? Then you can say they need to wait for the last batch to finish. You say there is a long tail, right, for the shuffle stage, for the reduce stage, even after 800 seconds, right? You say almost there is no activity, but still need to wait until the last set to finish. Right? This makes this job finish roughly 50% slower than the normal operation. The last one, they try to say they kill 200 processes. Now you say you first have the map and then you kill them, then you need to do something again, right? But still, it's almost finished at the same time. So they can, this is for MapReduce sort. So basically, to summarize, the technologies used here, right? So for replication, it's using Google file system and the eraser coding for storage. And the sharding and the partitioning, those used for both Google file system and MapReduce tasks. Load balancing for both of them. And health check for both of them. Integrity check for both of them. Compression, Google file system, they do use some compression if needed. And the eventual consistency, this is using Google the GFX master. Centralized controller for both. And redundant execution using MapReduce. Okay, so summary. Right? So the key is used to manage wisely so that you can have your, especially for Google, right? They know their demand very clearly so that they can specialize their system for their demand. Second one is you should strive for simplicity, especially for users. Right? If you have ever used MapReduce, you will know that as a user, you only need to define the map and reduce function, right? So that all the other system details are hidden. But for those we discuss here, normal user, they don't need to know. The last one is fault tolerance and scalability are not optional, right? For large-scale system, you will have failure very often, right? You see in both systems, they can handle failure like smoothly. And scalability, right? That is very important if you want to scale out your systems to run on hundreds or even thousands of servers. Okay, so I finished this part. Any questions before we finish the lecture? Okay, if no more questions, I will see you next Tuesday.